When night falls and the city lights fade behind the horizon, the sky reveals itself as a vast ocean of stars. It is a sight that has guided explorers, inspired poets, and awakened philosophers for countless generations. Yet beneath the beauty of this endless canvas lies a question as old as humanity itself. Is life an extraordinary miracle unique to Earth, or is it a cosmic pattern written across the universe? Every age, from the ancient Greeks and Romans to the scholars of the East, has wondered whether other worlds might harbor life. That simple question has endured through centuries, whispering to us whenever we gaze upward into the darkness. Today, for the first time in history, we stand closer than ever to an answer. Spacecraft travel beyond our homeworld to study distant moons, while telescopes capture the faint glow of planets circling other stars. The search for life is no longer only myth or speculation, but a scientific pursuit grounded in evidence. Each discovery brings us a step nearer to unveiling whether life is a rare accident or a universal law. As we begin this journey together, let us carry with us both curiosity and humility. For the answer may transform not only how we see the cosmos, but also how we understand ourselves. For as long as human beings have looked up at the night sky, a single question has echoed across generations. Is life an extraordinary phenomenon that belongs only to Earth? Or is it something that the universe repeats countless times across the stars? From the first myths of ancient civilizations to the reflections of modern philosophers, this question has remained at the very center of our search for meaning. Yet, despite centuries of curiosity, there has never been a clear answer. The heavens have always inspired both awe and mystery, keeping their deepest secrets hidden just beyond our reach. The human imagination has never been satisfied with silence. The Greeks and Romans speculated about countless worlds. Chinese scholars imagined that the cosmos was filled with hidden realms. In the Renaissance, thinkers such as Giordano Bruno dared to suggest that stars were suns with their own planets, perhaps even with life. Each culture, in its own way, has asked the same question: are we alone? These stories and speculations reveal a deep truth about us. We are not only creatures who live, we are creatures who seek companions, even among the stars. For most of history, the stars seemed too distant, and the planets too unknowable. Telescopes brought us closer, but still left us in the dark. Even when Mars showed mysterious channels on its surface, later proven to be illusions, hope and imagination persisted. The silence of the universe could have been taken as proof that we are alone, but humanity has never given up. We continue to search, to listen, to build new tools. It is part of our very nature. We reach beyond the boundaries of what we know, even when the answers seem impossibly far away. Now, in our own time, something extraordinary has changed. We live in an age where space probes cross the solar system, landing on distant moons and planets. Sophisticated telescopes peer into the depths of the universe, gathering light that has traveled for billions of years. We can detect planets orbiting other stars, measure the chemistry of alien atmospheres, and even trace the faint whispers of molecules that may be the building blocks of life. The tools of science have carried us to a threshold that previous generations could scarcely have imagined. This is why the question feels different today than it did a century ago. It is no longer a matter of pure speculation or myth. With each mission, each discovery, we are brought closer to a moment of revelation. The search for life beyond Earth has become one of the greatest scientific journeys of our age. It is not only about finding microbes under Martian soil or oceans beneath icy moons. It is about discovering whether life is a universal rule of nature or a fragile exception. The answer will reshape how we see ourselves and our place in the cosmos. So, as we begin this story, let us carry that ancient question forward. We stand at a moment in history where the distance between imagination and evidence is shrinking. The universe is opening itself to our instruments, our mathematics, and our wonder. Perhaps the answer has been waiting all along, hidden in the light of distant stars or beneath the ice of a nearby moon. What was once a dream is now a scientific pursuit, and as we take the first steps into this journey, we may finally come closer than ever to knowing whether we are truly alone. For thousands of years, humanity could only wonder about the heavens with the naked eye. The stars seemed eternal, unchanging, and impossibly far away. Even with the invention of the telescope in the 17th century, what we saw remained limited to points of light and faint clouds across the night sky. The question of whether other worlds existed, and whether they might resemble our own, was beyond our reach. We lacked the tools to move beyond speculation. But the modern age of science has changed that, giving us instruments powerful enough to pierce the veil of space and time. The 20th century opened a new frontier with the launch of spacecraft. Machines built by human hands left the Earth and crossed the void, visiting the planets that had long been only mysterious lights in the sky. Probes flew past Mercury, Venus, Mars, and Jupiter, sending back images that revealed landscapes more alien and more familiar than we had imagined. The simple idea of building machines to leave our world marked a turning point in human history. Suddenly, the planets were not unreachable. They were places to be visited, studied, and perhaps, one day, inhabited. Yet, the greatest leap came not from what we sent outward, but from what we built to look deeper. Telescopes on Earth grew vast, their mirrors stretching wider, and their detectors becoming more precise. They no longer simply captured points of starlight, but uncovered entire galaxies hidden in the blackness. At the same time, astronomers developed clever methods to detect planets orbiting distant suns. By watching for the faintest dips in brightness as a planet crossed in front of its star, they could infer the presence of another world. This technique, called the transit method, was like noticing the shadow of a small insect passing in front of a blazing lighthouse hundreds of kilometers away. In the year 2009, the United States launched the Kepler Space Telescope, a mission that would redefine our place in the universe. Kepler stared at a single patch of sky, no larger than a clenched fist held at arm's length. Within that tiny window, it observed over 150,000 stars, recording each flicker of light. Whenever a planet passed across its star, the telescope registered a minute dimming. Over years of observation, these small shadows revealed an astonishing truth. Planets are not rare. They are everywhere. Before Kepler, astronomers had confirmed only a handful of exoplanets, and many still wondered whether worlds like our own were the exception rather than the rule. The data transformed that uncertainty into clarity. Kepler uncovered thousands of planets, ranging from gas giants larger than Jupiter to rocky spheres not much bigger than Earth. The conclusion was inescapable. The majority of stars have planets. In fact, there are more planets in the Milky Way than there are stars themselves. The discovery was nothing less than a cosmic revelation. This single leap in technology expanded our horizons beyond measure. If every star is likely to host planets, and if the Milky Way alone contains hundreds of billions of stars, then billions of Earth-like worlds may exist within our own galaxy. Multiply that by the more than 100 billion galaxies scattered across the cosmos, and the scale of possibility becomes staggering. The universe, once thought to be a vast emptiness, now appears as a garden of worlds, each with its own potential for seas, skies, and perhaps even living beings. For the first time in history, our instruments have given us evidence that the question of life beyond Earth is not a distant dream, but a real scientific frontier. Technology has acted as the bridge between imagination and discovery. Probes and telescopes are our eyes and ears, stretching our vision to the farthest stars and the smallest grains of ice. They reveal not only the abundance of worlds, but also the potential for a universe brimming with life. Humanity has taken a decisive step forward, and the journey has only just begun. For centuries, the stars were seen as distant lanterns, without certainty of whether they hosted worlds of their own. That changed dramatically in the last few decades. The Kepler Space Telescope, launched in the year 2009, transformed astronomy by staring at a small patch of the sky and patiently recording the light of thousands of stars. Whenever a planet crossed in front of its star, Kepler detected the faint dimming. Over years of observation, these shadows revealed a staggering truth. Planets are not rare. They are everywhere, outnumbering the stars themselves. This revelation created a profound shift in our understanding of the cosmos. The Milky Way contains hundreds of billions of stars, and Kepler's data suggests that most of them are surrounded by planets. Many are gas giants or barren rocks, but billions could be Earth-sized and orbiting within the so-called habitable zone, where liquid water might exist. Multiply that possibility across more than 100 billion galaxies in the observable universe, and the number of potential Earth-like worlds is almost beyond imagination. The question is no longer whether other planets exist, but how many of them may host life. Alongside this explosion of awareness came another breakthrough: the study of extremophiles on Earth. These resilient organisms thrive in boiling vents, frozen deserts, and acidic pools once thought uninhabitable. Their existence demonstrates that life can flourish in conditions far harsher than we ever expected. When paired with the discovery that planets are abundant, extremophiles change the game entirely. The cosmos is not simply filled with worlds. It may be filled with worlds where life, in some form, has already found a way to begin. When we first imagined life beyond our planet, we tended to think of Earth as the perfect model. The assumption was that living beings could only survive under conditions similar to our own: moderate temperatures, mild climates, gentle seas, and breathable air. Anything outside that narrow comfort zone was considered fatal to biology. A planet too cold, too hot, too acidic, or too dry was dismissed as sterile. Yet, in recent decades, discoveries here on Earth have overturned this belief. In some of the most hostile places imaginable, life does not merely survive, it thrives. These extraordinary organisms are called extremophiles. The word itself means lovers of extremes. They are microscopic pioneers that challenge our understanding of biology. Some of them flourish in boiling hot springs, where water rises far above the boiling point. Others cling to existence in frozen deserts, where the temperature falls well below zero for centuries. Certain species live in lakes so acidic they could dissolve metal, while others endure levels of radiation thousands of times greater than what would kill a human being. Each discovery expanded the boundaries of habitability further than we thought possible. Perhaps the most striking examples are found deep beneath the oceans, at hydrothermal vents, where the Earth's crust cracks open and superheated water gushes out, loaded with minerals and toxic chemicals. For centuries, scientists assumed nothing could endure in such a place, far from the life-giving light of the sun. Yet, when submersibles first visited these vents, they found entire communities of organisms living in total darkness. Bacteria fed on chemical energy, creating the foundation for ecosystems filled with tube worms, clams, and other creatures. Life had discovered another way to persist. Even the coldest environments on our planet provide surprises. In the Antarctic dry valleys, where the air is so frigid and dry that liquid water cannot persist on the surface, researchers found microorganisms hidden in thin films of salty water trapped between grains of ice. These microbes remain dormant for most of the year and awaken briefly when summer sunlight warms the surface. Their existence suggests that life could cling to existence beneath the icy crust of Europa or within the frozen soils of Mars, awakening only when conditions allow a trace of liquid water to form. Extremophiles also reveal how adaptable life can be to chemistry itself. Some species flourish in environments saturated with salt, while others thrive in alkaline lakes. There are organisms that feed on methane, or even use radiation as an energy source. On Earth, these forms of life remain small, often microbial, yet their strategies offer a map for what might be possible elsewhere. If life can reinvent itself under such punishing conditions here, then on a moon bathed in radiation, or a planet with exotic atmospheres, similar forms might already exist. The discovery of extremophiles has therefore revolutionized the very concept of the habitable zone. It is no longer just a narrow ring around a star where liquid water might exist on a planet's surface. It is an expanding horizon that includes subterranean oceans, hydrothermal fissures, icy deserts, and methane lakes. Our search for life must now be guided not only by what Earth is, but by what life has proven capable of becoming. In this realization lies both a scientific breakthrough and a philosophical reminder. The universe may be far more alive than we once dared to believe. Before we can truly ask whether life exists elsewhere in the universe, we must face a more fundamental question. What exactly is life? At first, the answer seems obvious. We recognize life in the trees that stretch toward the sky, in the birds that cross the horizon, and in our own reflection. Yet when scientists attempt to define life with precision, the task becomes far more complex. Life is not a single quality, but a tapestry of behaviors. The ability to grow, to respond to the environment, to transform energy, and to reproduce. Only when these traits combine do we begin to see the phenomenon we call living. One of the most powerful definitions comes from the perspective of evolution. Life, in its essence, can be described as a self-sustaining chemical system capable of Darwinian evolution. This means that life does not simply exist in a moment. It learns, adapts, and transforms across generations. Through variation and natural selection, simple molecules assemble into complex structures, and single cells diversify into ecosystems. What distinguishes life is not just chemistry, but chemistry endowed with memory, a capacity to improve itself and endure through time. Tracing life back to its origin on Earth reveals another layer of mystery. Geological evidence suggests that life may have appeared as early as 4 billion years ago, almost immediately after our planet cooled enough to form stable oceans. The early Earth was not a calm cradle, but a violent world of volcanoes, meteor impacts, and storms. Yet it was precisely within this chaos that the first self-replicating molecules may have arisen, taking advantage of the available elements and the energy released by a young, restless planet. The story does not end with Earth. The ingredients for life, carbon, hydrogen, oxygen, nitrogen, and other elements, were forged in the hearts of ancient stars. When those stars exploded, they scattered these materials across space, seeding the galaxies with the potential for biology. Long before Earth was formed, interstellar clouds contained simple organic molecules, and meteorites that fall to our planet today still carry traces of them. Some scientists propose that life's earliest sparks may have been delivered from beyond our world, in a process known as panspermia, where comets or asteroids transport microscopic seeds of life across the cosmos. Others look even further back, to the beginning of everything. After the great explosion that we call the Big Bang, the universe was only a few million years old when conditions allowed the first atoms of hydrogen and helium to form. Later, stars ignited, forging heavier elements, and the foundations of life began to take shape. In this view, the chemistry of life is not an accident, but a continuation of cosmic evolution itself. The question of life's origin becomes inseparable from the question of the universe's own beginning, as though biology is the natural flowering of matter reaching toward complexity. In the end, the attempt to define life is as much a philosophical journey as it is a scientific one. We may not yet know exactly how life began, nor whether it has appeared in countless other places. But what we do know is that the essential ingredients and energies of life are not rare. They are spread across the cosmos, waiting for the right combination of circumstances. To understand life is to recognize that it may be woven into the very structure of the universe, a possibility that invites us to continue searching with curiosity, humility, and wonder. When scientists search the cosmos for life, they cannot look for the familiar forms of animals, plants, or bacteria directly. Instead, they search for the basic conditions that allow life to emerge and endure. Across decades of study, three requirements have risen above all others as universal markers of habitability. They are the presence of a source of energy, the availability of essential organic materials, and a stable solvent in which the chemistry of life can unfold. Together, these three pillars form the foundation of every living system known to us. The first condition is energy. Life is a process of constant transformation, turning matter into forms that sustain complexity. On Earth, the primary source of this energy is sunlight, driving photosynthesis in plants, and ultimately fueling entire ecosystems. But sunlight is not the only possibility. Deep beneath the ocean, bacteria thrive on the chemical energy released from hydrothermal vents. These organisms reveal that life can adapt to many sources of energy, from starlight to geothermal heat to chemical reactions. Wherever energy flows, the potential for life increases. The second condition is the availability of organic materials, the building blocks of biology. Carbon is the backbone of these molecules, binding easily with hydrogen, oxygen, nitrogen, and other elements to create chains and rings of staggering diversity. Amino acids, lipids, sugars, and nucleotides, all of which form the architecture of cells, depend on carbon chemistry. Remarkably, such compounds are not limited to Earth. They have been found in meteorites, in interstellar clouds, and in the icy crusts of distant moons. This suggests that the raw ingredients for life are woven into the very fabric of the universe. The third condition is perhaps the most familiar: a solvent. Life's chemistry requires a medium in which molecules can move, collide, and react. On Earth, this universal solvent is liquid water. Water is abundant, stable, and uniquely capable of dissolving a wide variety of compounds. It allows reactions to occur quickly and reliably, sustaining the metabolism that keeps organisms alive. Without a solvent, chemistry would grind to a halt, While water is the best candidate, some scientists speculate that other liquids, such as methane or ammonia, might serve similar roles under the right conditions. What makes these three conditions powerful is not their isolation, but their combination. Energy without raw materials cannot build living systems. Organic molecules without a solvent cannot interact or replicate. Water without energy is simply a frozen ocean. But when energy, organics, and a solvent coexist in balance, the possibility of life emerges. Earth is the most immediate proof of this principle, but it may not be unique. The search for extraterrestrial life is, in essence, a search for the meeting place of these three requirements. In the solar system, this trio has guided exploration. Scientists look for worlds where liquid water might exist, where organic molecules may be present, and where energy can flow in a sustainable way. Mars, Europa, Enceladus, and Titan each meet some or all of these criteria, making them prime candidates for investigation. The discovery of extremophiles has widened this scope even further, showing that even minimal energy, scarce water, or unusual chemistry can still provide fertile ground for life. Each mission we launch is an attempt to trace this recipe in new and surprising environments. These conditions also shape how we think about planets around distant stars. The concept of the habitable zone describes the region around a star where temperatures allow liquid water to persist on a planet's surface. Yet water alone is not enough. Astronomers now study the chemical composition of exoplanetary atmospheres, searching for carbon-based molecules or unusual energy cycles. The foundational trio becomes the compass by which we navigate the endless variety of alien worlds, allowing us to distinguish barren rocks from living possibilities. The search for life is therefore not blind. It is guided by principles drawn from our own experience of Earth, but expanded by our growing awareness of life's resilience. Energy, organics, and solvents form a triad that is simple in description, but profound in implication. These conditions remind us that life is not magical, but natural, not a rare exception, but a likely outcome wherever the universe provides the right stage. In following this trail, we are not only searching for others, we are learning why life appeared here in the first place. Ultimately, the foundational trio is both a scientific framework and a philosophical insight. It tells us that life, in all its complexity, begins with simple necessities. It tells us that the same rules that shaped our world may shape countless others. And it tells us that the boundaries of habitability are far wider than once imagined. The story of life, then, is not only about where it exists, but about how it arises whenever the cosmos allows energy, matter, and a solvent to dance together. It is a reminder that we live in a universe primed for creation. Among all the worlds in the solar system, Mars has captured human imagination more than any other. For centuries, it appeared as a red dot wandering through the night sky, a planet that seemed strangely alive compared to its neighbors. Early astronomers saw dark streaks, and believed they were canals carved by intelligent beings. Writers of science fiction filled its deserts with alien civilizations. Although those fantasies have faded, the fascination has remained. Today, Mars is not merely a distant dream. It is a place we have studied closely with orbiters, landers, and rovers, a planet that continues to whisper the possibility of life. Mars presents a landscape that feels hauntingly familiar. It has mountains, valleys, canyons, polar caps, and dunes. Yet everything is harsher, colder, and more fragile than Earth. Billions of years ago, Mars was warmer and wetter, with a thicker atmosphere and flowing rivers. Vast canyons carved by water and minerals that form only in the presence of liquid reveal that the planet once held seas and lakes. Over time, as its atmosphere thinned and the planet cooled, those waters retreated beneath the surface or froze into ice. What remains is a desert world, scarred by the memory of a vibrant past. The search for life on Mars has been ongoing for decades. In the year 1976, the Viking missions carried out the first direct experiments on the Martian surface, testing the soil for signs of microbial activity. The results were controversial, with some scientists interpreting chemical reactions as biological, and others dismissing them as purely geological. In 1997, the Pathfinder mission delivered new insights, finding minerals such as magnesium, aluminum, and phosphates that could support life. Each mission built upon the last, gradually deepening our understanding of Mars and its hidden potential. In 2008, the Phoenix lander explored the Martian North Pole. Beneath just a few centimeters of soil, it found bright material that quickly evaporated. The analysis revealed it was water ice. This discovery confirmed that large quantities of water lie frozen under the Martian surface. Satellites later scanned the polar regions and discovered that beneath the carbon dioxide, frost caps lay vast reserves of water ice. If melted, the volume could cover the entire planet in a global ocean more than 20 meters deep. Mars, though dry on the surface, still hides enormous reservoirs of water. The story did not end there. In September of 2015, the Mars Reconnaissance Orbiter provided the strongest evidence yet that liquid water may still flow intermittently on the surface. Using an imaging spectrometer, researchers detected hydrated salts on slopes marked by dark streaks. These streaks appeared during the warm seasons and faded in the cold, suggesting briny water seeping through the soil. Though fleeting and salty, such water could offer niches where microbial life might endure. The dream of finding life on Mars was no longer confined to its ancient past, but extended to its present. Mars also holds mysteries in its atmosphere. Observations have revealed fluctuating levels of methane, a gas that on Earth is strongly linked to biological activity. While geological processes can also produce methane, the possibility that microbes beneath the surface release it has ignited scientific debate. Rovers like Curiosity have measured seasonal variations in methane levels, raising questions about whether Mars still hosts active processes, biological or otherwise. Each whiff of methane is a tantalizing hint, a signal that the planet may not be as lifeless as once believed. Extremophiles on Earth offer valuable clues about how life might survive on Mars today. In the dry valleys of Antarctica, microorganisms endure in thin films of water where ice meets soil. These microbes remain dormant most of the year and awaken briefly during warmer conditions. Similar strategies could allow organisms on Mars to persist within buried ice, protected from radiation and desiccation. Hydrothermal systems, heated by ancient volcanic activity, may also have created safe havens where microbes could have flourished. The analogs on Earth make the possibility of Martian life more plausible. Modern missions continue to search for these signs. The ExoMars program, a collaboration between the European Space Agency and Roscosmos, is designed to drill into the Martian subsurface in search of biosignatures. NASA's Mars 2020 rover, named Perseverance, carries instruments to study rocks and soils, seeking evidence of ancient microbial life. It also tests technologies for producing oxygen from carbon dioxide, preparing the way for human exploration. These efforts are part of a broader strategy to not only understand Mars, but also to uncover whether life ever took root there. The allure of Mars lies in its proximity and its similarity to Earth. It is close enough to explore with current technology and familiar enough to imagine walking on its surface. Yet, it is also alien, colder, drier, and more hostile than any desert on our planet. Its atmosphere is thin, its radiation levels high, and its resources scarce. If life ever existed there, it must have been resilient, clinging to niches of stability. To find even a fossilized microbe would be to prove that life is not unique to Earth, but a common thread woven into the cosmos. The exploration of Mars is more than science. It is a story of human curiosity. Each rover that traverses its plains, each orbiter that maps its canyons, is part of a journey to answer one of our oldest questions. Mars may yet reveal that we are not alone, that life has sparked more than once within a single solar system. Whether in the flowing rivers of its past or the thin brines of its present, the red planet holds the potential to transform our understanding of biology, of evolution, and of our place in the universe. The answer waits beneath its soil and within its rocks, and we are closer than ever to finding it. Far out in the cold reaches of the solar system, orbiting the mighty planet Jupiter, lies one of the most intriguing worlds we have ever encountered. This world is Europa, a moon only slightly smaller than Earth's own moon, yet wrapped in mystery and beauty. From a distance, Europa gleams like a pearl in the darkness, its surface bright and smooth, glistening with frozen water. Unlike the battered faces of most moons, Europa shows only a scattering of craters, as though something beneath its icy skin is constantly reshaping and renewing it. The fractures and ridges across its face form a vast network of lines, like a puzzle spread across a sphere. These strange features led scientists to suspect something astonishing. Beneath Europa's frozen crust might lie a hidden ocean. Evidence gathered by the Galileo spacecraft in the late 1990s confirmed this suspicion. As Galileo flew past the moon, its instruments detected a magnetic field that could only be explained if a vast ocean of salty water sloshed beneath the ice, conducting electricity in response to Jupiter's powerful magnetic environment. Estimates suggest that this ocean may be as deep as 60 miles, containing more water than all of Earth's oceans combined. But water alone is not enough for life. For life to persist, it needs an energy source. Here again, Europa offers a remarkable possibility. As Europa orbits Jupiter, its path is slightly stretched into an oval shape. This eccentric orbit means the moon is pulled and released by Jupiter's immense gravity, flexing its interior like a piece of soft clay. The friction from this constant stretching generates heat, a process called tidal heating. This internal warmth may be strong enough to keep the hidden ocean from freezing solid, and it could even drive hydrothermal activity on the sea floor. On Earth, hydrothermal vents at the bottom of the oceans are teeming with life. Bacteria cluster around hot springs, feeding on chemical energy rather than sunlight. Entire ecosystems of strange creatures, from giant tube worms to blind crustaceans, thrive in total darkness, nourished by minerals rising from the depths. If similar vents exist on the sea floor of Europa, where hot water meets rock, then the possibility of life is real. Simple microorganisms could have adapted to these environments, just as they have done in the harshest places on our own planet. There are further hints that Europa might possess the chemical ingredients required for life. Observations of its surface have revealed the presence of carbon dioxide, along with simple organic molecules that may form when radiation from Jupiter strikes the icy crust. Some regions of the surface even show clay-like minerals that may have arrived through ancient collisions with comets or asteroids. Such materials could provide the necessary building blocks for life, feeding the chemistry of the subsurface ocean and opening the door to the possibility of a second Genesis within our own solar system. The tantalizing nature of Europa has inspired new missions that will soon journey to this mysterious world. NASA's Europa Clipper, scheduled for launch in the middle of the 2020s, will perform dozens of close flybys. Its instruments will scan the surface, probe the thickness of the ice, and search for signs of water plumes that might vent material from the ocean into space. At the same time, the European Space Agency is preparing the Jupiter Icy Moons Explorer, or JUICE, which will travel to Jupiter and study several of its largest moons, including Europa, Ganymede, and Callisto. Together, these missions will open a new chapter in our understanding of Europa. They may reveal the chemical composition of the ice, detect signs of organic molecules, and perhaps even provide the first direct evidence of life beyond Earth. For the first time, we will have the tools to peer beneath the icy shell of this enigmatic moon and imagine what kind of creatures might inhabit its hidden ocean. If life exists there, It would prove that biology can emerge in environments far different from the warm cradle of Earth. Europa is more than just another moon. It is a reminder that the universe is not limited to the familiar. It shows us that beneath an icy surface, far from the warmth of the sun, a living ocean may thrive. The cracks and ridges etched into its crust are not just scars of geological stress. They are the fingerprints of a world alive with movement. And as we prepare to send new explorers across the void, we find ourselves on the edge of a discovery that could transform our understanding of life, not only here, but everywhere in the cosmos. Among the many moons of Saturn, one stands out as both tiny and extraordinary. It is Enceladus, a world only about 300 miles across, yet dazzlingly bright, its surface covered in brilliant ice that reflects the sunlight like fresh snow. At first glance, Enceladus seems quiet and lifeless, a frozen marble adrift in the cold vacuum of space. But when the Cassini spacecraft began its long mission around Saturn, it revealed that beneath this serene exterior, something astonishing was taking place. Enceladus was not a silent moon. It was alive with activity. Cassini's cameras captured images of the South Pole, and what they showed shocked scientists. Stretching across the icy surface were 4 enormous fractures, later called tiger stripes. These fissures were far from ordinary cracks. Thermal sensors detected that they were strangely warm, more than 100 degrees Celsius, hotter than the surrounding landscape. Instead of freezing solid like the rest of the moon, these regions seemed to be radiating energy into space. Something deep below was keeping them alive with heat, defying the bitter cold of Saturn's outer realm. The mystery deepened when Cassini flew closer. From the tiger stripes erupted towering plumes of water vapor and icy particles, fountains that sprayed hundreds of kilometers above the surface before falling back like shimmering snow. When the spacecraft passed directly through these geysers, its instruments captured samples. Inside the frozen spray, scientists discovered tiny grains of salt and even complex organic molecules. The presence of salt suggested that the plumes were connected to a vast underground ocean, and the organics hinted at the possibility of chemical processes similar to those that nourish life on Earth. The idea of an ocean beneath the ice of such a small moon once seemed unlikely. Enceladus is so small that it should have frozen completely long ago. Yet Cassini's measurements of the moon's gravitational pull revealed something remarkable. A density anomaly beneath the South Pole, consistent with a regional sea of liquid water. The constant tidal tug of Saturn bends and flexes Enceladus, generating heat in its interior just as it does on Europa. This process could create hydrothermal vents on the sea floor, where hot water and rock interact, producing energy and nutrients that might sustain life. If such environments exist, they could resemble the deep sea vents on Earth, where microbes flourish without sunlight. On our own planet, these vents are oases of life, supporting entire ecosystems in the dark. The same could be true for Enceladus. Microorganisms might drift in its subsurface ocean, feeding on chemical energy and leaving behind traces in the icy particles ejected into space. Unlike other hidden oceans, however, Enceladus gives us a direct window into its depths. Its geysers spray material into space, offering samples that spacecraft can capture and analyze without drilling through the ice. This accessibility has made Enceladus one of the most promising destinations for future exploration. Scientists have proposed missions that would fly through the plumes again, collecting particles to study their chemical makeup in greater detail. Some concepts go even further, suggesting probes that could capture samples and return them to Earth, where laboratories could search for the signatures of life with unparalleled precision. None of these missions have yet been approved, but the dream remains alive. The technology exists, waiting only for the decision and the resources to send it forth. Enceladus reminds us that appearances can deceive. What seems like a frozen wasteland may in fact conceal a thriving ocean, warmed by the pull of gravity and enriched with complex chemistry. The discovery of its geysers turned this tiny moon into a beacon for astrobiology, a place where the search for extraterrestrial life could yield its first success. As we continue our journey outward, the plumes of Enceladus rise like silent signals, urging us to come closer, to sample their icy spray, and perhaps to discover that life has already taken hold in one of the most unlikely places in the solar system. Beyond the glowing bands of Saturn, one moon stands apart as a world of its own. Titan, larger than the planet Mercury, and shrouded in a dense golden haze, is unlike any other place in the solar system. From a distance, it appears as a muted orange sphere, its surface forever hidden beneath a thick atmosphere of nitrogen and hydrocarbons. Yet when the Cassini spacecraft arrived at Saturn in the year 2004, it released a small probe named Huygens that drifted down through the fog. As it descended, cameras revealed a landscape of mountains, valleys, and wide plains that looked eerily similar to Earth, as if a frozen twin world had been waiting in the outer dark. When the Huygens probe touched down on Titan, it made a discovery that astonished scientists. Scattered across the ground were countless rounded shapes resembling river pebbles, the kind one might expect to find on a stream bed here on Earth. But these were not rocks of silicate and granite. They were blocks of water ice, frozen so hard in Titan's frigid environment that they behaved like solid stone. Even more extraordinary were the radar scans from Cassini, which revealed hundreds of lakes and seas across Titan's surface. These bodies of liquid did not contain water, but methane and ethane, gases on Earth that, under Titan's temperature of nearly 180 degrees Fahrenheit degrees below 0 Celsius, become liquid and flow like rivers. This discovery unveiled a world with a methane cycle that mirrors the water cycle of Earth. On Titan, methane evaporates into the atmosphere, forms clouds, condenses, and falls back as rain. It carves channels, fills lakes, and shapes valleys in a process strikingly familiar, yet entirely alien in substance. This parallel invites a profound question. Could methane, in this extreme cold, act as a solvent for life in the same way water does for us? Chemistry suggests that reactions in liquid methane would occur far more slowly, but the presence of abundant organic molecules in Titan's atmosphere hints at the possibility of unusual pathways to life. Experiments on Earth have shown that when simple gases such as methane and nitrogen are exposed to ultraviolet radiation, they can form complex organic compounds called tholins. On Titan, such processes are happening naturally, coating the surface with a reddish material rich in carbon. These substances may represent precursors to life, molecules that could, under the right conditions, evolve into self-replicating systems. Titan may therefore be a window into the past, showing us a world that resembles early Earth billions of years ago, before life truly began to flourish. The fascination with Titan has inspired ambitious mission concepts. Among them is the idea of a robotic submarine that could one day plunge into the depths of Kraken Mare, Titan's largest sea, to explore its alien waters. More recently, NASA has approved the Dragonfly mission, a revolutionary rotorcraft designed to hop across the surface of Titan like a drone. It will explore dunes, icy plains, and methane lakes, sampling chemistry and searching for signs of prebiotic processes. If successful, Dragonfly could reveal not only the secrets of Titan, but also provide a glimpse of how life might arise in worlds far different from our own. Titan stands as a reminder that habitability is not confined to Earth-like conditions. Its freezing methane seas, thick orange atmosphere, and icy geology suggest that the universe may host forms of chemistry and perhaps even life beyond what we can easily imagine. As we prepare to send new explorers to this world, we are reminded that discovery often comes not from familiar places, but from the most alien landscapes. In Titan's dark skies and liquid methane lakes may lie the keys to understanding life's infinite creativity. On Earth, life has proven itself to be far more resilient than we once believed. For a long time, scientists thought that living organisms could exist only in environments resembling the gentle balance of our planet's surface, temperate climates, liquid water, and mild conditions. Yet discoveries over the last few decades have rewritten that assumption. Deep beneath the oceans, within boiling volcanic vents, and even inside radioactive waste, tiny creatures have been found thriving. These are the extremophiles, organisms that flourish in extremes of heat, cold, pressure, or chemical hostility. Their existence has expanded the very definition of what it means for a world to be habitable. No longer can we limit our imagination to Earth-like conditions. If bacteria can endure temperatures above the boiling point of water or survive in pools as acidic as battery acid, then perhaps life could also take root in the methane seas of Titan or in the salty plumes of Enceladus. Extremophiles remind us that life is not fragile but adaptable, capable of bending the rules we once believed were fixed. They open the door to worlds we once dismissed as barren, now reimagined as possible homes for biology. Perhaps the most important lesson of extremophiles is philosophical. They reveal that life is not a delicate exception, but a persistent force, endlessly creative in its strategies. This resilience challenges the way we think about the cosmos. Instead of asking only where conditions resemble Earth, we are compelled to ask a deeper question. What other forms could life take, and what unfamiliar landscapes might already harbor it? By pushing the boundaries of what we call habitable, extremophiles show us that the chances of life beyond our planet may be far greater than we ever allowed ourselves to believe. Armed with this new understanding, humanity is preparing to explore the solar system with renewed purpose. Robotic explorers are already rewriting the history of our neighboring worlds. The ExoMars program, a partnership between Europe and Russia, seeks to drill beneath the Martian surface in search of ancient biosignatures. NASA's rover, Perseverance, launched in the year 2020, now roams the Red Planet, analyzing rocks and soils for evidence of past microbial life, while testing technologies that may one day allow astronauts to breathe Martian air. Beyond Mars, attention turns toward the icy moons of Jupiter and Saturn. NASA's Europa Clipper will soon embark on a mission to perform dozens of close flybys of Europa, scanning its fractured crust and sampling the material from its potential plumes. The European Space Agency is preparing the Jupiter Icy Moons Explorer, known as JUICE, to explore Europa, Ganymede, and Callisto, searching for water, organic chemistry, and signs of habitability. Proposals also exist for spacecraft that could capture particles from the plumes of Enceladus and return them to Earth, where laboratories could search for the fingerprints of life with unmatched precision. The horizon of exploration does not end with robots. The long-term vision of space agencies around the world includes preparing for human missions to Mars. Such journeys would represent one of the greatest undertakings in the history of our species. To survive on the Martian surface, astronauts will need to produce oxygen from carbon dioxide, harvest water from ice deposits, and develop ways to generate energy in an unforgiving environment. These technologies are not only steps toward survival on Mars, but also toward humanity's expansion into the wider cosmos. As we look to the future, the search for life becomes inseparable from the story of human exploration. Each mission, each probe, and each rover adds another piece to the puzzle. With every discovery, the idea of a living universe grows more plausible. The question that haunted philosophers and poets for millennia may soon have an answer, not in myths or dreams, but in data returned from other worlds. Whether we find microbes beneath the Martian soil, in the oceans of Europa, or in the methane seas of Titan, the revelation will change how we see ourselves forever. This realization carries a weight that is more than scientific. Even the discovery of a single microbe beyond Earth would forever alter our understanding of what it means to be alive and what it means to be human. It would reveal that life is not a fragile exception, but a cosmic principle, repeating itself wherever the conditions are right. The red deserts of Mars, the icy oceans of Europa, the geysers of Enceladus, and the methane seas of Titan are no longer just remote curiosities. They are reminders that we may be part of something much larger, perhaps one thread in a vast and living universe. And so the ancient question remains, but now with a new hope. Are we truly alone, or are we on the verge of discovering distant companions in the cosmic night? If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.